In this problem, we're gonna be looking at rolling motion. So what we have here is three different objects. We have a sphere, we have a cylinder, and we have a ring. So we're gonna place these three objects on top of an incline, and we're gonna let them roll down. There is a coefficient of static friction between them and the surface of the incline. And it's because of that static friction that we're gonna be talking about rolling motion here. These objects are not going to slide down, they're going to be rolling down the incline. Now, the question that we're gonna try to answer here is which one of these three objects is going to get to the bottom of the incline first? Which is the one that wins this race? So to answer this question, we can answer a very related question, which is which of these three objects reaches the bottom with the highest velocity? Which one has the biggest velocity at the bottom? So that's a question that is about the velocity at the bottom of the incline. So thinking about velocity, one of the concepts that is related to velocity is kinetic energy, and therefore thinking about conservation of energy. So to start writing equations for this, you can assume that you know the mass of the objects, you know the radius, we know the height from which the objects are going to fall, and we're going to be trying to figure out what is the velocity as a function of those variables. So one thing to keep in mind is that the fact that we have static friction here doesn't mean that there is going to be dissipation of mechanical energy. Only when there is kinetic energy, kinetic friction, only when there is kinetic friction between two surfaces, that's when the two surfaces actually warm up and some of the mechanical energy gets transformed into thermal energy. But in this problem, we have static friction. For rolling motion, it's only necessary to have static friction. So static friction does not dissipate mechanical energy. Therefore, the role of static friction in a problem like this is to make sure that the linear motion is matched by rotational motion. So remember that for rolling motion, the bottom of the object is in contact with the surface and it doesn't slide on the surface. So that means that for these objects that are rolling down the incline, as they go down, the velocity of the center of the objects is going to be increasing. So if the rotational velocity doesn't increase at the same rate, then the object is going to start sliding. That is, the bottom of the object is going to be rubbing on the incline, and that will produce kinetic friction. But when an object rolls, that is static friction, and the force of static friction is able to guarantee that the rotational motion and the linear motion are matching each other in such a way that the object doesn't slide. So that is the reason why we can use conservation of mechanical energy here, because the role of static friction will be only to convert some of the kinetic energy of translational motion, convert some of that kinetic energy into rotational kinetic energy, but the energy is not lost. So we're going to apply conservation of mechanical energy between 2 points. The initial point will be at the top, the final point will be at the bottom. So as usual, we're going to say that the energy at the initial point equals the energy at the final point. At the top of the incline, we are letting this object start rolling without any initial velocity, so we only have potential energy at the top, mgh. At the bottom, when the objects reach the bottom, the objects are going to have kinetic energy, but they will have two forms of kinetic energy. One form will be the kinetic energy associated with the center of mass of the object moving, that is translational kinetic energy, and the other form of kinetic energy will be rotational kinetic energy. So we have 1/2 of mv squared, and we also have, at the same time, we have 1/2 of I omega squared. Translational kinetic energy and rotational kinetic energy together. So we have to add them to get the final velocity of the objects at the bottom. So these two, we're going to make these two initial energy and final energy equal to each other. And therefore, mgh equals 1/2 of mv squared plus 1/2 of I omega squared. That term, as we said, is the kinetic energy due to the motion of the center mass, and this term is due to the kinetic energy of the rotation of the objects. An object, when it's rolling, it's both moving translationally and also rotationally, so it has both forms of kinetic energy. So remember that for rolling motion, another thing that we know is that the velocity of the center of the object is related to the angular velocity of the object. I just mentioned that. The fact that for rolling motion, the bottom of the object doesn't slide, and that was discussed in a video. We concluded that the velocity of the center of the object has to be equal to the angular velocity multiplied by the radius of the object. That way, the bottom of the object makes contact with the ground with zero velocity. So there is a relationship between those two. So in the kinetic energy equations, the V and the omega are related through that equation. So what we're going to do is replace omega with V over R. So we have mgh equals 1/2 of mv squared plus 1/2 of I V over R squared. Now, to start getting to the point where we can distinguish between or see what's the difference in the velocity at the bottom due to the different shapes that these objects have, we're going to look at the moment of inertia and write the moment of inertia as a constant multiplied by the mass times the radius squared. Any object that has a circular profile will have a moment of inertia with this kind of equation. The c will be different, of course. So if you recall, for a disk, the moment of inertia with respect to the center mass was 1/2 of m r squared. For a sphere, the moment of inertia is 2/5 of the mass times the radius squared, and for a ring is just mr squared. So all of these three shapes have a moment of inertia given by c mr squared, where the c has a different value. So we're going to use this. We're just going to leave it in terms of c, and the equation at the bottom becomes mgh potential energy equals 1/2 of mv squared plus 1/2 of, the moment of inertia is now c mr squared, and we have the omega squared, which can be written as v squared over r squared. Notice that the radius of the objects cancels out. So surprisingly, the speed at the bottom is not going to depend on what the radius of the object is. And the masses cancel, so it doesn't matter what the mass of the objects is. The velocity is not related to that. So that's also a surprising result for this problem. So simplifying a bit, we have on the left hand side hg equals, on the right hand side, v squared over 2 and 1/2 of c v squared. Again, for the different shapes that we have, the c value is going to be different. So instead of solving this problem 3 different times, we're solving the problem one time, but this solution is going to cover all 3 cases by simply replacing in the equation c with a different value. So continuing to do a little bit of algebra here, we can write multiply by 2 on both sides, 2he equals, and we're going to factor v squared from both terms, and we get 1 plus c v squared on the right hand side, and solving for v, we get the interesting result, square root of 2he divided by 1 plus c. So something to compare with that is interesting is that if these objects had been sliding down the incline, if there was no friction whatsoever, then the velocity at the bottom, we've done this before, the velocity of an object sliding down an incline is the square root of 2hg. So we see that for a rolling object, the fact that some of the translational kinetic energy has to be converted to rotational kinetic energy leaves the object with less speed at the bottom. Less speed because the number c is always going to be bigger than 0. If it was 0, then the object will be sliding and the answer will be square root of 2hg. But once the object rotates, as the object rolls, the kinetic energy, there is kinetic energy of rotation, so we have a c, and that c value in the denominator is going to give you a smaller velocity than if the object had been sliding down the incline without rolling. So that kind of makes sense. From this equation, we can now finally answer the question that we set out to find out its answer, which was which one is, of the 3 objects, the sphere, the cylinder, and the ring, which one is going to win this race. So we have to find out which one has, at the bottom, the biggest velocity. But we have a velocity equation now. Clearly, from that equation, the fact that the c value is in the denominator tells us that the biggest velocity is going to be for the object with the smallest c. So comparing the c values, for a sphere the c value is 2/5 or 0.4, for a disk the value is 0.5, and for a ring is 1. So we arrive into the conclusion that in this race the sphere will win.